Hello everyone, welcome to the part 2 of the hyperconjugation series of videos. We have done the discussion about history and background in the part 1. Now we'll be talking about the order of the hyperconjugation, and there will be some classification based on different methods. We then will be having some other terms related to the hyperconjugation. So there are first order and second order of hyperconjugations. We will be seeing first of all what is the order and how we are recognizing it in comparison to the conjugation. Then when we'll be talking about classification of hyperconjugation, we'll be seeing there is something called positive conjugation and negative conjugation. Negative conjugation also we are calling as reverse hyperconjugation sometimes. That will be the basis of the direction of electron, in which direction the electrons are going. There will be another classification which will be on the basis of the number of valence bonds. We call that isovalent hyperconjugation and sacrificial or heterovalent hyperconjugation. And then there will be some related term we'll call homohyperconjugation. We'll be seeing that in a moment. So first of all, we will be talking about the order of hyperconjugation. First order conjugation we'll be seeing, and then when we have got second order conjugation, that is the thing what was called as hyperconjugation by Mulliken, my mistake. Then third order hyperconjugation we'll be talking about the same way. Here is the basically idea. What is the first order conjugation? This one. Then second order conjugation, and then third order conjugation. First order conjugation is the usual case of conjugation, what we might have seen earlier. This is usual case of conjugation where the electrons from the pi bonds, one of the pi orbitals can be going to another pi orbital. From pi orbital they can be going into p orbital, or non-bonding electron can also be going into p orbital or the pi bond. That kind of conjugations we have seen earlier. That is the case of normal conjugation. In second order conjugation, the conjugation is going to be even weaker, and importantly, the electrons which are being delocalized, they are going to be the sigma electrons. This kind of thing is what we have called as hyperconjugation. Please note, when we have got second order of the conjugation, that is considered as hyperconjugation. So when it will be coming to third order conjugation, that is what we are calling as the second order hyperconjugation. The difference in the usual conjugation what we are seeing and second order hyperconjugation what we are seeing here is, in this case the electrons are being delocalized into sigma star antibonding molecular orbital. Usually when the electrons are being delocalized, they are going either into the empty p orbital, singly occupied p orbital, or empty pi star bonding, antibonding molecular orbital, what we say. So these different cases we'll be seeing in our further discussion. I'll be showing one by one what one is the case of the second order hyperconjugation. And in fact, we'll be seeing the examples. This one is in the carbocation and free radicals. This one is in the alkenes. These we'll be seeing in different conformers and some other examples. We'll be talking of that in a bit. Then here we have got the thing what we are understanding as second order conjugation. Hyperconjugation we have been actually seeing in the introduction, that here the sigma bonded electrons which are present, those are going to be delocalized into the p orbital or pi star molecular orbital. This kind of conjugation, when sigma bonded electrons are going, they are being delocalized. This is going to be the second order conjugation or hyperconjugation. And this is very much natural that when we have got the electron donor ability and electron acceptor ability, if you have got the electron accepting ability of the empty orbital, if it is going to be greater, then this is going to be much better delocalization. Better the delocalization, greater will be the stabilization for the molecule concerned. Here we are seeing the example of carbocation, where empty orbital is getting the electron from the alpha carbon hydrogen bonds, and this is the case of radical where this singly like one unpaired electron which is singly occupied orbital is present on this carbon. There we are having the sigma electron being delocalized. These two cases are where we are going to say this is going to sigma to p conjugation. Next case is where sigma bond electrons are going into the pi star antibonding molecular orbital. That kind of conjugation is also considered as the normal hyperconjugation or the second order conjugation. That's the case what we are considering right now. This is the example, these are the cases when we will be considering this is the second order conjugation. Now, when we say third order conjugation, or when we're talking about the second order hyperconjugation, this is going to be the delocalization into the sigma star molecular orbital. Like this time, this is going to be the acceptor molecular orbital, empty sigma star molecular orbital when this is going to be the receiving orbital, or this is going to be acceptor, electron acceptor when this is sigma star. We are considering this is going to be the second order hyperconjugation. And again, that thing is going to be very much same. Better the electron donor ability, electron acceptor ability of the sigma star molecular orbital, better the delocalization would be, and better will be the stability. We have here some example of a molecule where we have got we call the molecule as methyl chloroform. So if you see here, this carbon hydrogen bonds are electron rich, and here there are the electrons present. These sigma bonded electrons can be delocalized, and these electrons can be basically delocalized into this carbon chlorine bond. There will be one sigma antibonding molecular orbital. Along this particular bond, there is going to be one sigma star antibonding molecular orbital. And because carbon chlorine will be having a relatively greater electron withdrawing nature in the carbon chlorine bond, so that just like this bonding molecular orbital electrons are more towards chlorine, the anti-bonding molecular orbital will be having much more tendency to receive the electron. That is what we are saying. The electron acceptor ability of the sigma star molecular orbital is going to be much better over here in the carbon chlorine bond, and carbon hydrogen bond will be having relatively electron donor ability. This one is going to be, the first case is going to be electron donor, this one, and here this one is going to be electron acceptor. So good electron donor, good electron acceptor, this kind of third order conjugation or second order hyperconjugation is going to be possible in this case of methyl chloroform. So the orbital where electrons are going to, that is sigma star, that defines the second order hyperconjugation. We have got one more example of second order hyperconjugation. This is the same example basically we have written with respect to the hyperconjugating structures. So when we are writing basically hyperconjugation, one of the bond is being shifted, we relate these kind of structures as hyperconjugating structures, just as we were talking about the resonating structure when conjugation was there, or sometimes we are calling that as the contributing structures. That should be relatively more correct term. So here what is happening, this molecule is having, CH3 is going to have basically quite delta positive charge, because those hydrogens are going to be having delta positive spread on this hydrogen, as well as on this. All these three hydrogens are going to have relatively delta positive charge, and all these three chlorines one by one can be having delta negative charge. So the net thing is we can have this whole molecule, this end can be having your positive charge and this end can be having a negative charge. There will be a net dipole moment present along this direction, and this molecule will be having unexpectedly higher value of the dipole moment than what we can think about by the addition of the vectors using carbon hydrogen bond and carbon chlorine bond. Like in any other example, if you have got carbon chlorine bond and carbon hydrogen bond, and if we do the addition, vector addition of those all vectors, this value cannot be justified. We have to take into consideration this kind of second order hyperconjugation, then only we can explain that what we call as unexpectedly higher value of the dipole moment. Okay. I hope you are getting it, that how the hyperconjugation is modifying the property, and this is the relatively weaker type of hyperconjugation, or we sometimes say second order hyperconjugation. Okay, so now we will be talking about the classification. Our classification will be based on these three things. Number one, direction of electron transfer. Number two, the change in the number of bonds which are being formed, and this will be seen with respect to valence bond theory. And then there is going to be the nature of the orbitals involved. Here we may need to look into the molecular orbital theory. Direction of electron transfer, we can see with respect to the valence bond theory only. The orbital representation we will be requiring, and we'll be seeing one by one how these kind of classifications are there. So first, we are saying this is on the basis of the direction of electron transfer. Second one is the basis of the number of bonds formed, and the nature of orbitals involved we'll be taking further in the details in the next slide. So these two we are taking up here. First one is, when we are saying direction of electron transfer, there can be a positive hyperconjugation or there can be a negative hyperconjugation. This positive and negative will be related with respect to the direction of the electron transfer with respect to CH bond. And then in the number of bonds formed, there are two types, isovalent or heterovalent. Heterovalent is the same thing what we will be recognizing as sacrificial hyperconjugation. And nature of orbitals when they are involved, where these electrons are coming from, like which electrons are basically there which are undergoing delocalization. That is also one possible mode of classification. We'll be seeing that sigma electrons are going into empty orbital, pi electrons are going into empty orbital, and non-bonding electrons are going into empty orbital. That's how we can classify the hyperconjugation. Here is that third conjugation what we were saying there. So when we have got sigma electrons going into empty orbital, we will be coming back to all these cases one by one. First of all, I'm explaining this what kind of the orbitals are involved here. So when we have got sigma electrons involved, this is actually the most frequently seen hyperconjugation what we might have seen or which we might be applying in different applications. So sigma bonding electrons can be going into the p orbitals. Sometimes these will be going into the pi star molecular orbitals, and sometimes this will be going into the sigma star molecular orbitals. So let us say carbon hydrogen sigma bonded electrons are being delocalized. When there is a case of carbocations and free radicals, here we are seeing this is going to be sigma to p hyperconjugation. But when it comes to the case of alkenes or even alkynes, alkyl benzenes as well, if that's the case, then sigma bonded carbon hydrogen electrons are going into the pi star antibonding molecular orbital, that is pi antibonding basically molecular orbitals. These carbon hydrogen bonds the carbon hydrogen electrons can also be going into the sigma antibonding molecular orbital, just as we have seen in the second order hyperconjugation just earlier. And this kind of situation we have seen, one case was this methyl chloroform. Other alkyl halide can also have the same thing. Also there will be the case of the conformers of ethane will be seeing. There also will be understanding how the sigma star hyperconjugation is going to be present. Then pi bonded electrons are also seen to be involving hyperconjugation, and we have one very well known case where these electrons are going into the sigma star, that is sigma antibonding molecular orbital, and that's the case of the allyl halides. And also this is going to be the case of benzyl halides like benzyl chloride or benzyl fluoride. There we can have this kind of hyperconjugation observed. We have non-bonding electrons also, they can be going into empty orbital, and this is one example we can see here, which is the non-bonding electrons are going into the sigma star, that is sigma antibonding molecular orbital. Those sigma star antibonding molecular orbitals can be belonging to carbon hydrogen bonds. They can be belonging to some carbon heteroatom like nitrogen oxygen fluorine bonds as well. That changes from cases to cases. One example we'll be having in methyl glucopyrroside, and that is what we sometimes be calling as the anomeric effect. The anomeric effect. This. So we'll see one by one how these different electronic delocalization are going to take place and how these different kind of classification are there. First, hyperconjugation we have classified into the direct with respect to the direction of electron transfer. Some we are calling as positive and the other one we are calling as negative. When we have got positive hyperconjugation, then this is the electrons which are going to be involved. Let us say we are talking about the electrons which are present in the CH bond. These electrons will be pushed. They will be giving their electron density. So when such a kind of a bond is present which is giving its electron density to this hyperconjugated system, we understand this is going to be plus H effect in the same lines as we have talked about the plus I effect, that is inductive effect, and plus M effect also we are saying sometimes, that mesomeric effect, or plus R effect rarely we are saying. The same way, when we have got electron withdrawing effect, that can be the case at least when we are talking about some carbon chlorine bonds, just like we have seen in methyl chloroform, or will be seeing in benzyl chlorides in the reverse hyperconjugation. So this carbon chlorine bond will be having the effect that if there is a hyperconjugated system present along with it, this will be having a nature of pulling electron towards itself, that electrons will be pulled towards this, and this thing will be having the nature of electron will be pushed, electron will be given from this. That is how these two, positive hyperconjugation and negative hyperconjugation, should be recognized from each other. Here we have an example of the positive hyperconjugation. So we are saying if you have got so many of the alkyl group present, usually we will be seeing this will be the alpha carbon hydrogen bonds, which are mostly being delocalized as the result of hyperconjugation, and that can be happening into empty atomic orbital like p orbital. It can be happening into singly occupied p orbital, or it can be happening into antibonding molecular orbital. We have got this kind of electron donating effect whenever present. We are calling this as positive hyperconjugation effect. Here we are showing that you have got some carbocation, and in this carbocation, this empty orbital what we are having over here, in this empty orbital, electrons from this alpha carbon hydrogen bond, these electrons we have shown, these electrons from the alpha carbon hydrogen bonds are being delocalized into this orbital. So with respect to this CH bond, this is going to be our electron donating effect, and this electron donating effect we are recognizing as plus H effect for this CH bonds which are present onto the alpha position of the respective systems. Like here we have got that positive charge where this delocalization is going to take place. In the radicals or other kind of systems, we can be having different kind of conjugated or hyperconjugated, we should say more clearly. Hyperconjugate systems can be there, and the CH bond is going to have electron donating effect. Now, just like we have seen that plus H effect in the carbocation, we can see that like in fact the same example, positive hyperconjugation we are seeing, and we have shown here when we have got the case of the alkene, there also positive hyperconjugation is there. Alkyl benzene can also be having hyperconjugation, and we can see here when the one compound, one structure or one species is undergoing hyperconjugation, then how the next structure when we are writing, we will be using this kind of sign which we have been using just in the resonating structures. So this alpha carbon hydrogen bonds are being delocalized into this empty orbital, and when that is happening, we will be losing this hydrogen as H plus. This molecule will be having actually this hydrogen being lost, and there will be double bond formation taking place here. That is what is the case of positive hyperconjugation. The another example, this is basically the same example we have talked about the carbocation only, but these other molecules are also known to have the alkenes, and alkyl benzenes are also known to have the same kind of hyperconjugation, positive hyperconjugation of plus H effect possible. We have then negative hyperconjugation. In this negative hyperconjugation, we need to have some group which will be having electron withdrawal tendency. That's when you have got relatively quite polar bond where the more negative atom is present onto the terminal side, like chlorine is carbon chlorine bond can be present, even carbon oxygen bond can be present, carbon nitrogen bond can be present. Those kind of bonds can be having quite electron withdrawing abilities. If there are suitably situated other systems, these electrons can be pulled by these kind of antibonding molecular orbitals. That is what is happening in this negative hyperconjugation. We also call this as sometimes reverse hyperconjugation, and that is because this is going to be operating in the reverse direction to what was there in the usual case of the conjugation. And this we'll say it will be excited by the sigma bonded electrons of the alpha haloalkyl group. We can see one kind of system, like just like we were calling about we were saying in the normal conjugation, alpha CH, that is hydrogen bond, was involved in the hyperconjugation. Here we can say alpha carbon halogen bond can be involved in that same kind of interaction, same kind of delocalization, and that can be nearby to the some alpha carbon hydrogen bonds present. It can be nearby to some pi bonding molecular orbital present, or it can be even near to something where can be non-bonding electron pair present. There also it can be present. That can be also with some of the non-bonding electrons. Lone pair we could have said basically. Yeah, so here we have got one example. The fluorine which is present, that will be demanding electron from the carbon. Carbon will be having electron deficiency, so the antibonding molecular orbital, what we say, which will be basically more like the carbon, that will be having quite electron deficiency. So that empty antibonding molecular orbital can be pulling electron from this non-bonding electron pair, and if that is happening, this kind of first that Lewis structure what we have drawn would be converting into the second kind of Lewis structure, and that fluorine is being given off and this compound is converting into alkene. Interestingly, this is the step number 2 what we have seen happening in the even CB mechanism when the alkyl fluorides are undergoing elimination. This is just one aspect of negative hyperconjugation. Like there we can tell why the fluorine is going to leave and can it leave easily. Answer is yes, although it is going to be relatively poor leaving group, but this negative hyperconjugation or reverse hyperconjugation can be helping the carbon fluorine bond to be broken rather easily than otherwise what we could have anticipated. Another example for the negative hyperconjugation we can see that is coming from the alkenes. So that pi bonded electrons can be going into the antibonding molecular orbitals where we have got the electron demanding group. So in alkene, if the alpha carbon is having at least one of the halogen atoms present, we can have this kind of situation possible. So say if this was the carbon atom and say this was the halogen atom over here, if this was a chlorine over here, the orbital what we have shown here is the sigma star antibonding molecular orbital. Basically the sigma star is empty and the electrons which were present over here in this carbon double bond, these electrons are being basically delocalized. That chlorine is pulling that electron withdrawing effect is considered as negative or reverse hyperconjugation minus H effect we can say. The another example we have just seen in the previous slide, that was with respect to the valence bond diagrams. Here we are trying to see with respect to the molecular orbital diagrams where this negatively charged carbon having the electron present in sp3 hybrid orbitals, this is being delocalized onto the, that is again we can say this is carbon and this is chlorine, and this kind of orbital is again going to be the sigma star antibonding molecular orbital. There these electrons are being delocalized. This electron withdrawing nature of this carbon chlorine sigma star orbital is considered as the reverse hyperconjugation or the negative hyperconjugation. Coming to the next type of classification, we have got isovalent or heterovalent kind of hyperconjugation. This is with respect to the number of bonds which are present when we are writing two different structures written after the delocalization. The focus is on the number of bonds. Are these values changing? If they are changing, iso, that is same. And if they are hetero, different, it is heterovalent. And heterovalent is basically also called as sacrificial. The reason is at least one of the bond is being sacrificed. If you say sacrifice, that means there should be less number of bonds. So when we say isovalent hyperconjugation, this is the same number of the bonds which are present earlier in our molecule, and in the next structure which we are writing after hyperconjugation, there also we are having the same number of the bonds present. That happening, we are calling this as isovalent hyperconjugation. And we can also see the structure which we will be drawing just after this. We will see that is going to have kind of double bond and no bond resonance kind of situation, but the total number of bonds are not changing. See here, the ethyl carbocation we have seen there are total 6 bonds present. 1 carbon-carbon bond and 5 carbon-hydrogen bonds are present. But as a result of hyperconjugation, if we are delocalizing these electrons from carbon hydrogen bonds over to this empty orbital of the carbon, then what is changing? This hydrogen is being lost as H plus over here, and then this pi bond is being formed over here, this one. When the pi bond is being formed, the total number of bonds are not changing. 4 carbon hydrogen bonds are present and 1 carbon-carbon single bond and another carbon-carbon pi bond. Basically the pi bond we have to count here separately as a different bond. That's why in the beginning we have said this is supposed to be considered with respect to the 2 electron bonds. So pi bond is separate, sigma bond is also 1 2 electron bond, and another pi bond also is 1 2 electron bond. Sigma and pi bond should be counted separately for that when we are considering the isovalent hyperconjugation or even heterovalent hyperconjugation. So this is how they will be counting the number of bonds in this valent type of classification for hyperconjugation. I hope that's clear, right? See, now when it comes to heterovalent, the thing is the valency is not going to, not valency basically, the number of the bonds which we see are not going to be same. And because it is sacrificial, then the one bond is being less. So that normal 2 electron bond what we are talking about, this is at least 1 bond less in comparison to the first structure when we are trying to do or trying to show the delocalization of electrons taking place. And rightly said, because one bond is being sacrificed for the sake of hyperconjugation, we are calling this as sacrificial hyperconjugation. See here, we have got propene and total 9 bonds we are having here. Out of those 9 bonds, there are 3 carbon-carbon bonds and 6 carbon-hydrogen bonds. Out of those 3 carbon-carbon bonds, one of this bond is pi bond over here, and 2, one of this and one of this are carbon-carbon single bond, like sigma bonds. Total, out of total these 9 bonds, when we are doing the hyperconjugation, we are shifting this electron here and this electron here. What we are getting? We are getting total 8 bonds left. One of this bond what is being broken over there, and one bond what is broken over here. In lieu of that, only one bond is being formed. So out of 9 bonds, 1 bond is missing now. That is what we mean to say by sacrificial hyperconjugation or the heterovalent hyperconjugation. Right? That is one of the terms we might not be using very much frequently, but if we are seeing with respect to the number of valence bonds, we can classify this either of the two, isovalent or heterovalent. Now going to the number of the nature of orbitals involved, we have got this classification once again. We have talked about this thing already. What are going to be the cases for the carbocations or free radicals? What are going to be the cases for the alkenes and alkyl benzenes? So basically sigma bonding electrons going into p, pi star or sigma star are going to be the cases of the carbocations, alkenes and your methyl chloroform or alkyl halide, those situation. And then when sigma bonded electrons were going into the pi star molecular orbital, that is what we have just seen was the case of the benzyl halide or the alkyl halide. Also, we can see the non-bonding electrons also can be going into the pi star. Methyl glycosides are one of the examples. We'll be seeing that in the cases of anomeric effects in detail later. Just to have an idea how these kind of examples are there. So we have got the first example where we have got the carbon sigma to p bond, like sigma p conjugation when the sigma p hyperconjugation when that's taking place. We have got the examples of carbocations and radicals. When we have got sigma to pi star, we have got alkenes and alkyl benzenes, and when you get sigma to sigma star, this is going to be case of the methyl chloroform or the alkyl halide 7 alkanes as well. We'll see the examples of these. So that is these two first cases onto the left. This is for carbocation and that is for the radical. This is sigma to p conjugation, basically hyperconjugation basically, and this is the case of alkenes. And what we have shown here is this antibonding molecular orbital. So this is going to be the case of alkene, where we are going to have the sigma to pi star hyperconjugation. We are seeing this on the basis of just the orbitals involved when this kind of electrons delocalization is taking place. And I hope you might have noted already, when this is a single electron present in this orbital in the case of radical, then the direction of this arrow we are keeping is different than what we are otherwise using in the case of normal delocalizations. And this is the case when the electrons of the sigma bonded electrons are going into the sigma star antibonding molecular orbital. That kind of situation is also going to be there in the case of hyperconjugations. Next example is going to be where sigma electrons are going into the empty molecular orbital. So just one case we are having here, that is benzyl chloride or situations like that. We have just shown here one chlorine. We can have even more chlorine. Similar situation will be arising there as well. So what was happening here? This is filled pi molecular orbital, like occupied molecular orbital. This is there, filled pi molecular orbital, and here we have got empty sigma star. So electrons are going from the pi orbital into sigma star orbital. That is the case of the benzyl halide, and that is basically one of the case of the reverse or negative hyperconjugation as well, what we have just seen. We also have the orbitals which can be involving from non-bonding electron to the empty orbital as well. Two examples we are going to take here. One is going to be the case of the ethers, we can say. Another one is going to be the case of the what we understand as the we can call as acetal, or derivatives of the acetals can be understood as the glycosides. So here is the first example. This is the like alcohols or ethers we can understand. Basically we have got Z heteroatom which is having a lone pair. It can be either of the ethers or it can be amines. Amines we can understand, maybe any other example we can think. We need to just replace this one of the valence, whatever this structure we have drawn, one of these bonds we can replace with the lone pair, then it can be the case of ethers, and right now this can be the case of amines as well. So what was happening? This non-bonding electron which is present on this heteroatom Z, this is going into this anti-bonding carbon hydrogen molecular orbital. And please note, when we are saying the electron acceptor ability, carbon hydrogen bond has very small electron acceptor abilities. This kind of delocalization will not be as much effective as it would be when the sigma star orbital is going to be quite electron demanding, something like carbon chlorine bond, something like carbon fluorine or carbon oxygen bond. Those are going to be quite electron demanding. This kind of hyperconjugation can be very much effective in those cases. Here, although it happens, but the extent of delocalization is going to be quite smaller. The stabilization what can be coming, it will be significant but not that much as it can be in case of highly electron demanding or the orbital which is having very high electron acceptor ability. Depending upon that, the extent of hyperconjugation can be changing, right? Another example we have taken, this is the case of, say, if you put here basically oxygen, if you put here oxygen atom, then this is going to be the case of glycosides. that is, we can say acetals in fact. So there, if you have got oxygen this time here, like this is going to be a carbon-oxygen bond. So this carbon-oxygen bond will be quite electron demanding. This kind of delocalization can be quite dominant. And this will be bringing in quite higher stabilization in comparison to this kind of situation. This is going to be quite electron demanding. If this is more electron demanding, that means there will be better electron condensing ability. This is electron demanding, but this is relatively less electron demanding. That sigma star orbitals, what we are talking about. You might have already noted how we have shown the sigma star molecular orbital for the carbon hydrogen bond and how we have shown it for the carbon oxygen bond. You have understood the molecular orbital diagrams, how the different orbitals, when they are interacting, which kind of the molecular orbitals will be formed. I need not explain here. If you have any difficulty, you can refer to that molecular orbital theory once again. There are a few other terms which also we need to consider. We'll be talking about homoconjugation, homohyperconjugation, and double hyperconjugation. So for these terms, basically, first we need to understand the homoconjugation. This is not truly related with the hyperconjugation, but understanding this homoconjugation will be a basis for understanding how homohyperconjugation is going to take place. And this term homo, what is basically coming in between, this is implying that there is some non-conjugating group coming in between. Like there is one pi orbital and there is another pi bond. Between these two, there is some non-conjugating group. It can be CH2 group, it can be any other group which is coming, which is not having any empty orbital, which is not having any orbital where lone pairs can be present, or it not having any of the orbital which can be allowing the electrons to be propagated from its left onto its right. Now, if we are considering the carbon-carbon pi bond and there is another empty orbital and there is methylene group in between, that CH2 group we call as methylene group, if that group is coming in between, then the conjugation across those two bonds, like usually when we are seeing this kind of conjugation, then what we have seen, the way we have been writing it, there was a carbon-carbon double bond, there was a carbon, there was one single bond, and here there could have been one empty orbital where the delocalization was possible. This was the case of conjugation, right? Here, the conjugation in this case was taking place across one sigma bond. But in homoconjugation, this conjugation is taking place across two carbon-carbon single bonds. So basically, what we are saying, if in comparison to this situation, we are having something C double bond C, there is one carbon, basically we are saying this extra CH2 group is coming, another carbon is there, and then there is one carbon which can be having some empty orbital. Now, if we can say that these electrons present onto extreme left, if they can be in conjugation with that, this is going to be the case of homoconjugation. How that happens? Let's have a look. The simplest example we might have encountered already is the cyclopropyl methyl carbocation. How that happens? See, there is one CH2 group present over here in between. This CH2 group, what is present in between, it appears that the CH2 might not be allowing this electrons to undergo conjugation, but that's not the case. When we have seen this stability of the cyclopropyl methyl carbocations, sometimes we are using a term called the dancing resonance. That dancing resonance is basically what? This is conjugation across this kind of bonds which are present here. So if you say there is one CH2 group present and across that CH2 group there is a delocalization possible, electrons can be moving from one side to another one, we can think about this electron being delocalizing over that. That is happening. This is the new bond formation what is taking place. This is the new bond what has been formed, and this carbon onto the extreme left is getting the positive charge. The question is, where else this kind of conjugation we can see? Well, it can be wherever this kind of steric demands are there, or wherever these kind of orbitals can be bent. In this case, if you remember one thing, we said that three-membered rings are kinetically favored. When we use that word kinetically favored, what we basically imply that if we have got one empty orbital present over here onto this right carbon where there was basically the positive charge present earlier, there is one empty orbital present there. And this electron density, if this electron density can be shared across that, this can be shared from here to there, then formation this three-dimensional resin and this orbital, they are quite closer. So closing that orbital and forming this kind of three-membered ring is quite probable, and this does happen. And if the reactions are taking place under, we say, some kinetically controlled conditions, then this three-membered ring are basically formed. Number of examples we know, and there is one very much popular example of the bicyclobutane being formed in one of the Wurz reaction pattern when we are having that 1,3-dihalocyclobutane being reacted. There we have this reasoning that the three-membered rings are kinetically favored. That is why that kind of thing is happening. So this can explain the other way around. If we have this kind of system, we have got cyclopropyl methyl carbocation, this positive charge can basically be shared. This positive charge can be shared across these different bonds. Like we can have this kind of structure, we can say, when we have got the orbital picture, we understand in this orbital overlap, this orbital can be sterically very much easily approachable to that empty orbital sterically. So if that is happening, this orbital will be left with the positive charge, and there this kind of overlap is going to take place for the formation of three-membered ring. And we have done here this bond deliberately that way because you remember cyclopropane does not have the straight bond where electron density should be lying along the internuclear axis. This is a little bit bent bond. Sometimes we also call it banana bond. Not actually that kind of banana bond what we have seen in the diborane, which was 3-center 2-electron bond. This bond is, although the one of the type of bent bonds, but this bent bond is normal 2-center 2-electron bond. This is unlike diborane. Sometimes we call this bond also as the banana bond, just like we have been calling those bent bonds of the diborane as well. Okay, so we have got another example of homoconjugation. Here we have got another such molecule. There is one carbon present, and now see here, this is not actually always necessary that CH2 should be present. That CH2 can be replaced by any other such species where there is no empty orbital present, no lone pair present. This carbon is basically having all the 4 sigma bonds present over here. So this orbitals and these orbitals now can be having the delocalization, which we can say is going to be classified as homoconjugation. In such a case, if we draw basically the orbitals, say if you have got some of the orbital present over here like this, and some of the orbital was present over here, something like that. This resin over here is going to be overlapping very easily. This is what we understand as one of the very much famous case of the homoconjugation. One more example of homoconjugation is coming. And this is the situation where we have written polyphenylene methylene compounds. These are basically polymeric species, and the homoconjugation can be stabilizing these molecules up to much better extent than we might be otherwise thinking. So see what is happening. There is one extra CH2 group present over here, and this CH2 group is not involving in not allowing basically conjugation to take place, but we can say homoconjugation is definitely going to take place. These two orbitals will be overlapping over here. This overlap we'll be calling as homoconjugation, and here also this electron delocalization can be possible. That is again going to be homoconjugation. And because these molecules are always going to be like that, in one case one type of symmetry of these orbitals will be undergoing overlap, and the another side, if you say with respect to this ring, phenylene ring, one side one kind of symmetry of orbitals will be overlapping, and the other side the other symmetry of the overlap is going to take place. This is going to be alternating in this kind of polyphenylene methylene type of molecules. And now comes the example of homohyperconjugation. In this homohyperconjugation, the thing which was happening in the previous examples, it was with respect to conjugation. The electrons present in p orbitals were being basically delocalized. Now, when we're talking about homohyperconjugation, this would imply the alpha CH bonds which were used to be earlier present. Now, the electrons which are present, the alpha, the carbon hydrogen bonds which used to be present, we can say sigma bonded electrons, there can be non-bonding electrons, there can be a pi system. This is undergoing hyperconjugation with any of the system, again where there is an intervening CH2 group. CH2 group is coming in between, which is not allowing that usual cases of the hyperconjugation to take place. This situation we are considering as homohyperconjugation. So whenever we have any case of the carbocation, we can be having the cases of alkenes. There is one extra CH2 group present, and then the very next carbon is having carbon hydrogen bonds. There also hyperconjugation is possible. So just like we were saying in the conjugation earlier case, here we are having hyperconjugation, we should say. This time this hyperconjugation is possible over two carbon-carbon single bonds. The next carbon hydrogen bond can be undergoing hyperconjugation. See an example. We have got this kind of three carbons we are having. So this carbon hydrogen bond, what we are having onto the right, this carbon hydrogen bond can be undergoing the hyperconjugation with respect to this empty orbital. So if this electron is say being transferred onto the other side, okay, so basically that electron, if it is undergoing that hydrogen electron is basically being shifted, and that one CH2 group was supposed to be present in between. That is the case of the homohyperconjugation. Another example we can possibly see, this is the case of some silicon based compounds. So what is happening in this case, we have got the positive charge present over here, and this is one CH2 group present. The CH2 group can have hyperconjugation possible from the alpha carbon hydrogen bonds, but then onto the next carbon, here there is one carbon silicon bond present, and we understand carbon silicon bond, there is a greater difference of electronegativity than it was in the carbon and hydrogen. What I'm saying is, if you have got carbon hydrogen bond, polarity over here, the delta negative charge what was there, delta positive charge what was there on the hydrogen. If you compare this with respect to carbon and silicon, this time this carbon is going to have greater delta negative charge in comparison to here. Basically delta of electronegativity is greater with the carbon silicon bond. We can say that this carbon is going to have a greater delta positive charge, and this carbon is having a greater delta negative charge. This situation is there. So this is having much greater electron donation ability in comparison to when there was a carbon hydrogen bond. So this electron can be sharing its electron density onto this empty orbital. And again, if you see, this time we are having this first carbon-carbon bond and second carbon-carbon bond. So this is happening across two carbon-carbon single bonds, just like we have seen in the case of homoconjugation. This hyperconjugation is taking place from the carbon, which is beta carbon. Earlier we used to have alpha carbon hydrogen bonds which were involving in hyperconjugation. Here we are having beta carbon hydrogen or carbon silicon bonds which are undergoing hyperconjugation. This is one of the cases of the homoconjugation possible. And what the result is going to be here, again you can see we have just talked about this. 3-membered rings are kinetically favored. Cyclopropane is going to be formed. Silicon loses 1 electron. Silicon is going to have a positive charge. This kind of structure, just like a carbocation, silicon based ion will be generated. Adamental Carbocation is our last example for the homohyperconjugation, and that is the last thing we are going to the second last thing. Basically after this we'll be talking about the double hyperconjugation and then we'll conclude. So we have got homohyperconjugation in the Adamental Carbocation. Adamantane is actually one of the basic building blocks of the diamond, and the hyperconjugative delocalization here is taking place across beta carbon hydrogen bonds. That term we could have introduced actually, and when we say normal hyperconjugation, we are saying alpha carbon hydrogen bonds are being delocalized. In homohyperconjugation, we can say there are beta carbon hydrogen bonds which are being delocalized, and this is understood. This is along across or through the non-hyperconjugating CH2 group. So adamantane was one of the basically 3 6-membered rings are joined together. This kind of molecule we are seeing is the Adamental Carbocation. You remove that positive charge from here, just put one hydrogen over there, over here, that is adamantane, the basic building block of the diamond. All the carbon would be tetrahedral. If you remove this hydrogen, you start joining there with the next such 6-membered rings. That is how the diamond is basically generated in 2 dimensions. Never mind. Coming back, in this Adamental Carbocation, what is happening, the positive charge which is present in carbon, it is supposedly not stabilized because we understood something we call as the bridgehead. Positive charge on bridgehead is not stabilized. That is what we had learned somewhere earlier when we were talking about the stability of the carbocation bridge. So we talked about things like that. Fine. Positive charge cannot be stabilized by the other kind of mechanisms, but the way we have been talking about the hyperconjugation or the other situations or the resonance like that. But here, if you have got beta carbon present, we have shown over here in this case, if this beta carbon is giving its hydrogen, this hydrogen we have just removed as H+, this carbon is forming one of the bond. That bond is going to give us again 3-membered ring. And as we understand, 3-membered rings are kinetically favored, although this may not be giving it very much thermodynamic stability. But the 3-membered ring closure will be providing that carbon, definitely completion of its octet, that will be providing it stability, and that does make this Adamental Carbocation to be stabilized. Not that just this one hydrogen can be doing so. All these 3 hydrogens, hydrogen number 1, hydrogen number 2, hydrogen number 3 can be doing so. So we can be having in all 4 such hyperconjugating structures possible. 1, this starting one, and 3 more where we are getting these 3-membered rings being formed as extra stabilization coming for that carbon, positive charge being transferred over to hydrogen. And it may be a little bit, we can see it's a resonant hybrid, rather we should say hyperconjugating hybrid. That kind of structure is going to be where the positive charge will be basically shared by the 4 atoms. 1, that carbon of the Adamental, that backbone, and 3 hydrogen atoms which are present under the beta position. There is this positive charge being delocalized. To have a much better idea, if we see with respect to the orbital overlap situation, we can see how the charge can be delocalized much easily. So this is the basically orbital overlap diagram that will be helping us understand how the delocalization of bonds is taking place, how the structure is becoming stable. Have a look. This was the first structure we have started with. One of the bridge which was coming above is hiding somewhere in these orbitals. So this is the basically the orbital situations. So we can see that empty orbital, what is there onto this carbon of the adamentyl backbone, this orbital can be in position to overlap with this orbital, as well as with this orbital. So when this hydrogen is going off as basically H+, this electrons will be going onto these orbitals, and those orbitals can be very easily forming bond with this kind of carbocation. That can be happening here, that can be happening here, that can be happening here as well. So if we are removing those hydrogens, basically we can be breaking these bonds in the first step, let us say, and then we'll be forming these bonds somewhere else. These bonds we can be forming onto this position, we can be forming onto this position, we can be forming onto this position. And if that is happening, we have seen basically the resonance hybrid earlier as well. This is the kind of resonance hybrid we can be forming, and that is how we are understanding this homohyperconjugation in adamentyl carbocation is stabilizing it in comparison to what we might have thought the instability what is there in the bridged carbocations, where the positive charge is present on the bridge head. There these compounds are basically usually unstable. They are not very much stabilized. Here quite stability is coming with respect to the normal otherwise bridgehead carbocations. The homohyperconjugation or the beta hyperconjugation, we can say, maybe that is going to be stabilizing factor for this adamentyl carbocation. Last term for the day, we are having the double hyperconjugation, and as the name is suggesting, there will be twice the hyperconjugation possible in the same molecule. When we say twice hyperconjugation, we mean to say there can be two carbon hydrogen or carbon-carbon sigma bonds. Basically, two sigma bonds would be moving in a fashion as in conjugation. If there are many of the double bonds, all those double bonds can be delocalized. We can say, for example, if we have got some molecule something like this, double bond, double bond, double bond, then if we are writing the resonating structure, what we can say is if this bond was moving, this bond moved, and at the same time this bond also moved. So just like here, the more than one bonds we were able to move. The same way hyperconjugation is also known, at least in certain cases, where more than one sigma bonds can be moving at the same time in the same delocalization process. Let's have a look how that can be possible. So this can be made possible if we are having relatively much better electron donor groups, and silicon is going to be our favorite choice. So what we have shown here is this was the first level of hyperconjugation possible, although we have been emphasizing here in most of our examples that hyperconjugation is taking place from carbon-hydrogen bonds. That's not always true. It can be happening through carbon-carbon bonds as well. The only difference is the carbon-carbon sigma bond having its electron donor ability is way smaller than the carbon-hydrogen because of the polarity or polarization in those kind of bonds what we have seen. And we have seen in previous discussion that carbon-silicon bond is having much greater polarity in comparison to carbon-hydrogen. That's why it is much better electron donor. So see what is happening here. Although the very first delocalization what is happening here in this case, that is coming from the carbon-carbon bond. This bond is basically a carbon-carbon bond, and this delocalization is not going to be very much efficient. But this delocalization is being made more effective by the use of double hyperconjugation. How double hyperconjugation? You understand, if this kind of hyperconjugation just has taken place, then what we are getting? We are getting this structure. And there is an alkene basically formed. This part as being fragmented, we can say as alkene ethene is being formed. But now what we are having, Can't we see very good possibility of hyperconjugation because silicon is there and the silicon carbon bond can be undergoing hyperconjugation much more readily than, and otherwise we can say in comparison to another carbon hydrogen bond could have shown the hyperconjugation. So this second hyperconjugation is kind of pushing this first hyperconjugation process. This first hyperconjugation, the carbon-carbon bond where this is being delocalized, which otherwise is very less likely to take place, or this is wherever it is happening, this is having much smaller effect than the normal alpha carbon hydrogen hyperconjugation. This is being facilitated by what? By this second hyperconjugation, what is happening. So this step plus this step, both if you put together, this is what we are calling as double hyperconjugation. If we put it together, this is what we are getting the same time. So we need to understand that this kind of delocalization is pushing this kind of delocalization to go through, and ultimately we are getting these products. Basically, this kind of delocalization is going to take place, and this is how we can be getting the fragmentation reactions may be possible, or this is basically how the double hyperconjugation can be operating. The idea was this hyperconjugation, this one, which was otherwise very much less likely to take place, can be made effectively possible by the presence of carbon silicon bond onto the next position. So these are all the cases. We'll be having then the references and all. These are all the references I have used for the information and secondary references. That's all for the day. We'll be meeting up in the next lecture. Thanks for watching. Please let me know about your thoughts in the comment section. We'll see in the next session about some of the more facts and the results which were from the Baker-Nathan effect, and then we'll be going to in lecture number 4, the mechanism of the hyperconjugation, how it takes place, and we'll be giving emphasis on the molecular orbital theory after that. That's all for now. Thank you. Bye-bye. Take care.